In this next example, let's suppose we have a submarine sitting at some position x naught. And every 4.4 seconds, that submarine is going to send out a ping. So just a sound, ping. It's going to go off until, say, it hits something. Maybe a ridge or part of a coral reef that we don't want the submarine to hit. Well, if the submarine's just sitting still, we would expect to hear a return ping every 4.40 seconds. Now, we don't know, though, how long that first ping takes to get back. That's not some information we're going to have access to in this problem. This is also, by the way, how sonar works. You wouldn't have access to the information of how far away the other submarine is. You'd have to figure that out somehow. You would just know how often the pings return after the first one. So after we hear that first ping, if we're sitting still, we hear another one every 4.4 seconds. If we wanted to try to figure out this return time, we would need to know the distance and the speed of sound in water, which is something we could have access to. Let me just go look that up. Speed of sound in water. I'm going to call it c, because later I'm going to talk about the submarine's velocity v. 1,522 meters per second. If the submarine's sitting still, we should hear that first ping come back after it's covered twice this distance, because it has to go there and back, divided by the speed. Okay, so I'm just doing that using x equals v naught t, and then I'm solving for t. T equals x over v naught, if you think about the kinematics equations. Okay, so this is how long that return ping, that first ping takes to get back, and every ping takes to get back. What if the sub's moving? If the sub is getting closer to this thing, or if this thing is getting closer to the sub, the rules would be the same thanks to something called Galilean relativity. If these two things are getting closer together, then the return ping period would be shorter. And I'm using the word period. It just means how often something repeats. So the time between repetitions would be smaller. So let's say we were getting a time between repetitions, or a period, of 4.37 seconds. So this is our actual return period. That's what would happen if we were moving at some speed. But not just some speed, this would happen for a very specific speed. So let's see if we can figure that out. We want to know what the submarine's speed is. Well, this problem can get kind of complicated. So let's try to take it very slowly. I'm not going to do every algebra step explicitly, but I'm at least going to explain every thinking step. So I wrote down the time to return if the submarine is sitting still. So if t equals 0, this is how long it would take for a given ping to go there and back, because it has to travel that distance using the speed of sound in water. Can I write down the time it would take if the submarine has moved forward some delta x, which would just be equal to the sub's velocity times time? And this time, by the way, would be the same amount of time that the ping went there and back to our new position, because however long it took the sound to get back here is how long we've been moving forward for. So can I write down that t? Well, I can definitely write down the part of the t that's to the wall, because that's just my distance to the wall over the speed of sound in water. Now I need to write down how long it takes to get back to this new point. Well, it's going to involve this distance minus this delta x, which is just the speed of the sub times the time. And these are the same t. Remember, however long it takes sound to get there and back to my new position is how long I had to move forward. And we're still having sound travel at the speed of sound during that interaction. Okay, well, I don't know these t's. I don't know these d's. What can I do? I do know this thing. I do know t naught. So if I can somehow get this t naught in here, does that help me? Well, consider this. If I wrote down the ratio of actual return time to the submarine, to the return time if the sub were sitting still, that should be the same ratio as our actual pings return time over the, or return period over the period if we were sitting still. And to the reported number of digits here, we have 3 digits. If I do this out, that's 0.993. So if I can somehow get t over t naught, or t naught over t, which would just be 1 over this, into this equation, then things will work out for me. So I need to get 2d over c. One thing I could do is say, oh, well, this is half of t naught, but I noticed because of the way fractions work, I could actually pull out this d over c and add it to this term. Let me show you how that works. So t is d over c, and then because this is subtraction over a denominator, I can split that up. Because think about if I just wanted to simplify this, common denominators mean that I can just subtract the tops, or the numerators. So that means this is 2d over c minus vt over c. Well, that 2d over c is just t naught. So t equals t naught minus vt over c. And ultimately, I'm trying to get the t and t naught together. So let's get everything involving t and t naught on the same side. And also, I'm ultimately wondering what my v is. So I can also just try to isolate v, and that would get t, t naught, and c on the same side. We know c, so maybe that would be handy. Let's write that out. I'm not going to show you all the algebra steps here, just because I don't want this video to take forever. Right? So all I did was solve for v. And now I can distribute this 1 over t. So this is c times 1 over t, same thing. C over t is 1 over t times c. So I can distribute that 1 over t in here, and that would give me v equals t naught over t. T over t is 1 times c. Okay, now it's just v equals t naught over t is the inverse of this, so t naught over t equals 1 over t over t naught, which would be 1 over 0.993. So I have 1 over 0.993 minus 1 times 1,522 meters per second. And if I do that out, I get 10.4 meters per second. Handy, right? Ratios can be pretty powerful things. That's really all that happened here is we used the ratio of return ping to expected ping if we were sitting still, and multiplied that ratio through to get our actual speed. So we were traveling at 0.007 times the speed of sound in water, which is this. So 0.007 times that should give me about this. It's neat, and it's one of the handy tricks that work in relativity. And it's not too much more complicated if you're working with things near the speed of light. We then have to consider something called Lorentz contraction, but we'll leave that for the modern physics course.